The content in this video comes from pages 10 through 15 of your textbook, and it's meant to help you achieve learning objective number 5, which is to interpret a graph that shows changes in air pressure from Earth's surface to the top of the atmosphere, and to sketch and label a graph that shows the thermal structure or temperature structure of the atmosphere. In a moment, I'll ask you to pause the video and complete a very brief assignment. If you haven't already done so, it's a good idea to skim pages 10 through 15 while the video is paused. Then come back and watch the rest of the video, paying particular attention to the bold words, which should include the key terms listed here, and to the figures and their captions. Please plan to read the content more thoroughly before you attempt the online vocabulary quiz or the concept quiz for this chapter. Based on this picture, describe for me what you think happens to the air temperature as you get higher up in the atmosphere. As always, bring a quick response, bring your response to class the next time you're here, and we'll talk about this as a group. It's a good idea to pause now. Near the Earth's surface, the air temperature decreases at a relatively constant rate called the lapse rate, which is often close to 3.5 degrees Fahrenheit per 1,000 feet. So if you wrote down on your brainstorm a moment ago that temperature decreases with elevation, you're right on track. If you didn't, bring that contribution anyway, so we can talk about what other answers might be. If the temperature lapse rate is present, in other words, if the atmosphere's conditions are such that their temperature is decreasing at 3.5 degrees Fahrenheit per 1,000 feet, then the air temperature, and if the air temperature is 46 degrees at the surface, 0 feet, then the air temperature about 4,000 feet above the surface will be at freezing, and snow and ice may be on the ground. Until the 20th century, scientists believed that the air temperature decreased with height throughout the entire atmosphere until a value of absolute zero, a negative 273 degrees C, was reached at the outer edge of the atmosphere. In 1902, it was discovered that temperature does not decrease continuously with an increase in altitude. Results of more than 200 balloon launchings in that year led a French meteorologist to conclude that the temperature stopped decreasing and leveled off at an altitude between 8 and 12 kilometers, 5 and 7.5 miles. Subsequent radiosonde data confirmed that the atmosphere has 4 layers that can be distinguished based on the rates of temperature change. The environmental lapse rate is the rate at which air temperature decreases with increasing elevation. Because the environmental lapse rate can vary throughout the day or from one season to the next, it's very important to have frequent measurements of that rate. To determine the actual environmental lapse rate, weather balloons called radiosondes carry instruments aloft which transmit the data by radio wave back to weather stations that are equipped with radar units. These instruments permit meteorologists to make vertical measurements, which are called soundings, of temperature, pressure, and humidity in the troposphere. Sometimes shallow layers of air can be found within the troposphere, this closest, lowest layer of the atmosphere, where the temperature actually increases with height. These reversals are called temperature inversions, and they're an important phenomenon to know about before we talk about fog and cloud development. Atmospheric pressure is simply the weight of the air above us. At sea level, the average pressure is slightly more than 1,000 millibars. This corresponds to a weight of slightly more than 1 kilogram per square centimeter. So it's about 14.7 pounds per square inch. Obviously, the pressure at higher altitudes is less because there's less air above the ground. 1/2 of the atmosphere lies below an altitude of 5.6 kilometers, which is about 3.5 miles. At about 16 kilometers, or 10 miles, 90% of the atmosphere is below you. And above 100 kilometers, 62 miles, only a trace, a fraction of a percent of all the gases composing the atmosphere remain below you. At an altitude of 100 kilometers, the atmosphere is so thin that the density of air is less than could be found in the most perfect artificial vacuum at the surface. Nevertheless, the atmosphere continues beyond that point to even greater heights. So the graphic portrayal of pressure in this figure shows that the rate of pressure decrease is not constant. Rather, air pressure decreases at a decreasing rate with an increase in altitude. Boy, that's a lot of increases and decrease. I'm going to say that again. Air pressure decreases at a lower rate that gets even lower as you go higher up in the atmosphere until you're beyond an altitude of about 35 kilometers, which is 22 miles. At that elevation, any more decrease is negligible. To put it another way, the data illustrates that air is highly compressible. In other words, it expands as pressure is released and becomes more compressed, more dense with increasing pressure. Consequently, traces of our atmosphere extend for thousands of kilometers beyond Earth's surface. Thus, to say that the atmosphere ends where outer space begins is kind of arbitrary. It's not a sharp line. It's what they call a gradational line, a gradual line. So to a large extent, whether or not there's a line between the atmosphere and outer space depends on exactly what you're measuring. It's apparent that there's no sharp boundary with respect to pressure. The vast bulk of the gases, in a nutshell though, are close to the Earth's surface. Okay. I just skipped a mistake slide. It was an old version of this one. The bottom layer of the atmosphere is known as the troposphere. That's where we live, and that's where almost all of the weather occurs. We don't see clouds higher than the top of the troposphere. But temperature throughout this layer decreases with increasing altitude, except where there's a little bubble here of warm air, here or there. Throughout this layer of the atmosphere, the properties like temperature and pressure are readily transferred by mixing, by turbulence. The term troposphere was coined by another French meteorologist in 1908. It literally means where the region of the atmosphere where air turns over. And that's a reference to the vertical mixing of air in that zone. So if you imagine the Earth's surface as being the bottom of a riverbed, we would expect all the surface roughness. Here's a lousy little tree I'm drawing here. Here's another one. I know they look like arrows, but they're pine trees. As air encounters these obstacles, it's forced upward, right? And so the same thing happens with mountains. So we can see a vertical shift or kind of a turbulence in this lower layer of the atmosphere. The temperature decrease in the troposphere is called the environmental lapse rate. Okay, so here, this ELR, or environmental lapse rate, is the rate of temperature decrease with increasing altitude in the troposphere. So that for every kilometer we move up in the sky, we can expect to see a 6.5 degrees C temperature decrease. Here is the lapse rate in English units. So every 1,000 feet you climb in the atmosphere, you can expect the temperature to decrease about 3.5 degrees Fahrenheit. This is the normal environmental lapse rate. And I want to emphasize, though, that it's not really a constant value. It's an average value. And it can be highly variable from one day to the next or from one season to the next. And so we have to measure it pretty routinely. Thankfully, we have easy ways of doing that. Everywhere we have airports, airplanes can bring that information to us when they land or take off. The temperature decreases in the atmosphere throughout the troposphere to an average height of about 12 kilometers. Yet the thickness of the troposphere is not the same everywhere. That's what the other graph here is showing you, this graph. Okay. It can reach heights in excess of 16 kilometers, 10 miles, as long as we're someplace where the atmosphere is moist, where there's a lot of water vapor. We can see the atmosphere get to thicknesses of 16 kilometers. So the tropics, very thick troposphere. In polar regions, it's a lot smaller. So the thickness of those, in those areas, here's the polar tropopause, might be 9 kilometers, or about 5.5 miles, or even less. Warm surface temperatures and highly developed thermal mixing are responsible for that great vertical extent of the troposphere near the equator. As a result, the environmental lapse rate extends to great heights. So 10 miles high will still be decreasing temperature at a rate of about 3.5 degrees Fahrenheit per 1,000 feet. Despite relatively high surface temperatures below, the lowest tropospheric temperatures are found aloft in the tropics, not at the poles. Okay, so that means it gets very cold here in the poles, but even colder at the high elevations near the tropics. So the troposphere is the chief focus of meteorologists because it's in that layer that essentially all important weather phenomena occur. Almost all clouds, certainly all precipitation, as well as any violent storms, are born in that lower layer of the atmosphere. And so that's why it's often called, in sort of a slang way, the weather sphere. Going upward, you have a diagram very similar to this one in your textbook. So don't be disillusioned by the fact that I'm showing you this one. This diagram just shows up a little bit better on my PowerPoint slide, so I use it instead of the one that's in your textbook. Beyond the troposphere lies another layer called the stratosphere. Notice that to get to the stratosphere, we had to pass this line. The break between the troposphere and the stratosphere is known as the tropopause. And you'll see that, that pause at the top of the stratosphere too, and at the top of the mesosphere. Every time there's a boundary between two atmospheric layers, it's a pause. But beyond the troposphere is the stratosphere. The boundary between the two is the tropopause. Below the tropopause, remember, we see all that transfer of energy from the bottom to the top based on the turbulence. The air is flowing over mountains and obstacles and going up to higher levels. In the stratosphere, that stops happening. And so we show you the tallest mountain on the world in this diagram. This is Mount Everest, and the top of the tropopause just about coincides with the height of, or the elevation of Mount Everest. So we're way up high in the sky. In the stratosphere, the temperature at first remains almost constant for a while in this lower level. Up to a height of about 20 kilometers or 12 miles total. And then it begins a sharp increase, a very rapid increase that continues until the stratopause. And so the top of the stratosphere, remember, is the stratopause. And here we see increase in elevation, not so much of an increase in temperature, but then all of a sudden it starts to warm up when we get to this feature. Okay. Higher temperatures occur in the stratosphere because it's in this layer that the atmosphere's ozone is concentrated. Remember that the ozone absorbs ultraviolet radiation from the sun, and so consequently the stratosphere is heated by the sun. A large part of our heat on the surface comes from the presence of water vapor and greenhouse gases that trap long-wave radiation from the Earth. We don't have that water vapor in the stratosphere, and so the stratosphere is warmed by UV or solar radiation. Although the maximum ozone concentration exists between about 15 and 30 kilometers, the smaller amounts of ozone above that height absorb enough ultraviolet energy to cause higher observed temperatures. So just a few ozone particles up here, but enough that they do absorb the heat from the sun. The next layer up above the stratopause is the mesosphere. In the third layer, which is the mesosphere, temperatures again start to decrease like they did in the troposphere. Here's a decrease, and here's another decrease. So until throughout the entire layer, that decrease in temperature occurs until we reach the top of the mesosphere, which is known as the mesopause. The average temperature in this layer can be as low as 90 degrees C, which is a minus 130 degrees Fahrenheit. So that's minus 90 C at the top, minus 130 degree in Fahrenheit. The coldest temperatures anywhere in the atmosphere occur right at the mesopause, so right here. If that comes up, if you get asked that on a quiz, where's the coldest point in the atmosphere? Everyone should say mesopause. The pressure at the base of the mesosphere is only about 1/1000th of the pressure that we see at sea level, so around where we live. At the mesopause, the atmospheric pressure drops to about 1/1000th of that at sea level. So we go from 1/1000th at sea level down 3 orders of magnitude to become 1/1000th of the sea level pressure. And it's because the accessibility is difficult that the mesosphere is one of the least explored regions of the atmosphere. It can't be reached by the highest flying airplanes. It can't be reached by research balloons. And it's not accessible to the satellites that are able to orbit lowest in the atmosphere, in outer space. So I think it's probably, your generation of rocket scientists that are going to figure out how to use the drone technology to finally get information from that layer. The next layer is the thermosphere. So it's the fourth layer, and it extends outward from the mesopause, kind of off into space. It doesn't really have a well-defined upper limit. It's this area, this thermosphere, is the layer, it contains the tiniest fraction of the atmosphere's mass. And when the air molecules are so far apart and so spaced so sparsely in that layer that we start to see temperatures increase due to the absorption of very shortwave, high energy solar radiation by atoms of oxygen and nitrogen. So temperatures rise to extremely high values of more than 1,000 degrees C, more than 1,800 degrees Fahrenheit in the atmosphere, in the thermosphere. But such temperatures are not comparable to those experienced near Earth's surface. Temperature is defined in terms of the average speed at which molecules move. Because the gases of the thermosphere are moving at very high speeds, the temperature is very high. But the gases are also so sparse that collectively they possess only an insignificant quantity of heat. I know that's hard to wrap your brain around. For that reason, though, the temperature of a satellite orbiting Earth in the thermosphere is determined chiefly by the amount of solar radiation it absorbs and not by the high temperature of the almost non-existing air around it. So if an astronaut inside were to expose their hand, the air in that layer wouldn't feel hot. And if I have a hard time with it, I imagine most of you do too. But that's not something that I think we will lean on too heavily for the test. A quick word here, though, about the bottom layer of the thermosphere. In addition to the layers defined distinctly by the vertical variations in temperature, another layer is the ionosphere, and it's located in the altitude range between about 80 and 400 kilometers. So it coincides with the lowest portion of the thermosphere. It's an electrically charged part of the atmosphere where molecules of nitrogen and atoms of oxygen are easily ionized. So they all have a charge to them because they absorb high energy shortwave solar radiation. In that process, each affected molecule or atom loses one or more electrons and becomes a positively charged ion. And the electrons are set free to travel as electric currents. Although ionization occurs at heights as great as 1,000 kilometers, about 620 miles, and extends as low as maybe 50 kilometers or 30 miles, positively charged ions and negative electrons are most dense in the range from about 80 to 400 kilometers. The concentration of ions in that range is not great below that zone because much of the short wavelength radiation needed for ionization has already been depleted. In addition, the low atmospheric density at this level results in a large percentage of free electrons being swiftly captured by positively charged ions. So beyond that 250-mile ceiling, the concentration of ions is really low because of the extremely low density of the air. And because so few molecules and atoms are present, relatively few ions and free electrons can be produced. As best as we can tell, the ionosphere has no impact on our daily weather. But that layer of the atmosphere is the site of a really spectacular phenomenon, the aurora. This is a picture of the aurora borealis, or the northern lights. There's also a similar phenomenon in the southern hemisphere called the aurora australis, the southern lights. They appear in all kinds of different forms. Sometimes displays consist of vertical streamers in which there can be considerable movement. Other times the auroras appear just as a series of luminous expanding arcs or as a quiet glow that has an almost a foggy quality. The occurrence of auroral displays is closely correlated in time with solar flare activity and in geographic location with the magnetic north and south poles. So when we have solar flares, they're massive magnetic storms on the sun. They emit huge amounts of energy and great amounts of fast-moving atomic particles. As the clouds of protons and electrons from the solar storm approach the Earth, they get captured by the Earth's magnetic field, which in turn guides them towards the magnetic poles. And then as the ions sort of impinge on the ionosphere, they energize the atoms of oxygen and molecules of nitrogen and cause them to emit light. So the glow of the auroras is the result of that physical phenomenon. Ions approaching the ionosphere and energizing the atoms of oxygen and molecules of nitrogen. Because the occurrence of solar flares is related with sunspot activity, auroral displays increase conspicuously when those sunspots are most numerous. Okay, here is the concept check. Use the content provided on the Canvas site as well as outside external sources to verify that you can formulate answers to these questions. They shouldn't be too terribly tricky. If you can comfortably answer these questions, you're in great shape. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, a great first thing to do would be start a discussion on the Canvas site. Beyond that, come and ask me for help, and maybe I can add shed some light on your problems at a later date. But these shouldn't be too tough. They should be pretty easy for you guys to figure out.